Hello friends, welcome to engineering tutorial. So today we are going to resume our discussion on basic physics. So far we have discussed the various introductory concepts related to vectors, starting from their basic properties, the operations related to vectors, dot product, cross product, and those were involving two vectors. So in this video we are going to extend our discussion on that. So please watch all those videos related to the basic concepts associated with vectors first. So today we are going to discuss about another important operation of vectors, which is triple product. Okay, so obviously, as the name suggests, triple product, it involves three vectors. Okay, three vectors are involved, and triple product, it is of two types. First is scalar triple product. Okay, scalar triple product and vector triple product. Okay, like we have dot product and cross product, that is scalar product and vector product involving two vectors. Here also in triple product we have scalar triple product and vector triple product. So first we'll discuss about scalar triple product and then we'll go to vector triple product. So what is scalar triple product? So let us say there are three vectors. Okay, A vector, B vector and C vector. The scalar triple product, it is represented as A vector, B vector and C vector, like this, and it can be written as A vector dot B vector cross C vector. This is the first way. Another way is A vector cross B vector dot C vector. This. Either ways it is correct. Okay. So in the first way we have the first vector A vector, and then we have the remaining two vectors, the cross product of the remaining two vectors, and then B vector cross C vector gives rise to another vector, and then we calculate the dot product of the first vector and the cross product of the remaining two vectors. With the second way, same thing, but here first we perform the cross product A vector cross B vector, and that resultant vector, the cross product vector, we have dot product with the third vector. It obeys this principle because dot product is commutative, that is A vector dot B vector is the same as B vector dot A vector. So if we do this, we'll get the same result either way. So let us try to prove it. Okay, so here let's say A vector is A1 I cap plus A2 j cap plus A3 k cap. That is A vector. B vector is B1 I cap plus B2 j cap plus B3 k cap, and C vector is C1 I cap plus C2 j cap plus C3 k cap. Now, the scalar triple product is A vector dot B vector cross C vector. This, okay, like this. So first, let us calculate B vector cross C vector. So B vector cross C vector, that will be equal to how much? I cap, J cap, K cap, B1, B2, B3. We have already discussed cross product, okay, vector product, you can check it out. C1, C2 and C3. The X, Y and Z components. First, in the first row we have the unit vectors along X, Y and Z axis, and then the X, Y and Z components of the respective vectors in the proper order. First B, then C. So this becomes I cap into B2 C3 minus B3 C2, then minus J cap into B1 C3 minus B3 C1, then plus K cap into B1 C2 minus B2 C1. This, okay, this is the thing. This is what? B vector cross C vector. Now we have A vector equals to this much, okay, this is B vector cross C vector. And this is A vector. So now if we perform A vector dot B vector cross C vector, it will be equal to A1 I cap plus A2 J cap plus A3 K cap dot, okay, dot B2 C3 minus B3 C2 I cap, then B1 C3 minus B3 C1 J cap, okay, this is I cap, and then we have B1 C2 minus B2 C1 K cap, this. So in dot product we know that only the components with the common unit vectors, only those things are allowed, and the remaining I into j, I into k, j into k, that is all 0. Only I into I dot I, j dot j, k dot k, that is equal to 1, and the remaining I dot j, j dot k, k dot I, that is all 0. So this will be equal to A1 to B2 C3 minus B3 C2 minus A2 into B1 C3 minus B3 C1 plus A3 into B1 C2 minus B2 C1. This is the triple product result. Now we can write it in determinant form as this: A1, A2, A3, B1, B2, B3, C1, C2, C3. This is the expression of scalar triple product. This. Okay, this is the expression of scalar triple product. Now there are some properties. So basically scalar triple product is the determinant of the respective x, y and z components in the proper order. A vector, B vector, C vector means the first row we will have the x, y and z components of A vector. In the second row we have the x, y and z components of B vector. And in the third row we'll have the x, y and z components of the third vector, C vector. Okay, remaining things which are important is the properties, some of the important properties of scalar triple product is that suppose we write the three vectors in cyclic order, okay, A vector, B vector, C vector, okay, scalar triple product A vector, B vector, C vector, and then we write B vector, C vector, A vector, and then we write C vector, A vector, B vector. This. So this we can write first way as A vector dot B vector cross C vector. This we can write as B vector dot C vector cross A vector. This we can write as C vector dot A vector cross B vector. Okay, and then the second way, first the cross product and then the dot product, we can write it as A vector cross B vector dot C vector, then B vector cross C vector dot A vector, and here C vector cross A vector dot B vector. So now when the cyclic order of the vectors remain unchanged, okay, this is the cyclic form ABC, BCA, CAB. In that case the scalar triple product value also remains unchanged. It means this is equal to this. Okay, scalar triple product of ABC is equal to BCA and is equal to CAB, and here also same, this is equal to this and this also. Now here an interesting thing, see here A vector dot B vector cross C vector in the first way, and here we have B vector cross C vector dot A vector in the second way. These two are the same because dot product is commutative. Okay, the order of the vectors, they do not matter because B vector cross C vector will produce another vector. So basically it is dot product of two vectors. So here it is A vector dot B vector cross C vector, here it is B vector cross C vector dot A vector. Okay, this. Then here it is A vector cross B vector dot C vector, and here it is C vector dot A vector cross B vector. Again dot product is commutative, so both of them, they are the same. Then here we have B vector dot C vector cross A vector, and here we have C vector cross A vector dot B vector. Again these two, they are the same. Okay, so either way you write it, it does not matter. Okay, this is the first property, and then the another property. Okay, so there are many properties which are not required, we'll only discuss those which are very important. Then is, let's say we write again the three vectors in three cyclic forms, that is A vector, B vector and C vector. Okay, this. Then we write B vector, C vector, A vector. They are all equal, but we are writing it, okay? And then we have C vector, A vector, and B vector. All these forms of scalar triple product, they have the same value because the cyclic order has remained unchanged. ABC, BCA, CAB. Okay. Now, suppose we write it here in reverse order. ABC, we write it here as C vector, B vector, A vector in the reverse order. Here we write it as A vector, C vector, and B vector, and here we write it as B vector, A vector, and C vector. Okay, this. Then they will be equal in magnitude but opposite in sign. They will be equal in magnitude but opposite in sign. Why? Okay, so let us write A vector, B vector, C vector, the scalar triple product. Let us write it as A vector cross B vector dot C vector. Okay, it is alright to write it in this way. Now the reverse order, C vector, B vector, A vector. Now let us write it as first vector C vector dot B vector cross A vector. Okay, it is also permissible to write it in this way, first the dot product then the cross product. Now we know that, let us say we have two vectors, P vector and Q vector. The cross product P vector cross Q vector, P vector cross Q vector, that is equal to minus of Q vector cross P vector. When their order is reversed, the sign becomes negative. We already know that. So when we apply that rule here, it becomes C vector dot minus A vector cross B vector. Okay, this C vector, B vector, A vector, we wrote it as C vector dot B vector cross A vector, and then we manipulated using this rule of dot cross product. We wrote B vector cross A vector as minus A vector cross B vector. So this becomes minus C vector dot A vector cross B vector. Okay, this. Or we can write it as minus A vector cross B vector dot C vector. Okay, it is allowed because dot product is commutative. Cross product is not commutative, the negative sign comes, but dot product is commutative. Okay, A vector dot B vector is same as B vector dot A vector. Okay, so here we use the same principle to manipulate it in this way. Now this here is nothing but minus of A vector, B vector, C vector, the scalar triple product of A vector, B vector and C vector in the order which is mentioned, first A, then B, then C. So we have proved that C vector, B vector, A vector triple product is equal to minus of A vector, B vector, C vector. So when the cyclic order of the vectors is reversed, magnitude stays same but sign is negative, minus. Okay, but magnitude stays same. Then another important property which will come in handy is that, let us say, while calculating scalar triple product, any of the two vectors are the same. Okay, let us say a vector, b vector. We have like this two similar vectors, equal vectors, a vector, a vector. So this will be equal to a vector cross a vector dot b vector. Now we know that when two vectors are in the parallel, they're equal, they're in the same plane or something, their angle between them is 0, and cross product is the sine of the angle between them, it comes into play. Now as the angle between them is 0, so sine 0 will be 0, and hence the net result will be 0. 0 dot b vector, and that will be equal to 0. Okay, this, the result will be 0. So when two vectors are equal, the scalar triple product, it vanishes, it is equal to 0. Okay, so these are some of the basic properties associated with scalar triple product, and this is the basic concept. So when we have the scalar triple product, this is the basic representation of scalar triple product in this proper order: A, B, C. First the x, y and z components of A, then the x, y and z components of B, and then the x, y and z components of C. Okay, this.